Okay, so what's happening today? We're going to basically we're going to do half of the proof of homological stability for configuration spaces. So today, hopefully, we'll get through stability for Rn. The idea of the argument is you sort of prove it in the Rn case and then use the Rn case to prove the general case. And so the main tool is compactly supported cohomology and Functoriality, which we touched on last time, but we'll review that. And then we'll talk about symmetric products, and then hopefully we'll prove homological stability for configurations of points in R2. Yeah. Okay. So the ordered configuration space is just the set of distinct points in M to the K, or tuples where each entry is distinct, which we're going to think of as like K distinct points in M. M will always be a manifold, and the symmetric group acts by permuting the order of the tuple. So you get the unordered configuration space, which is just the quotient by the symmetric group, and so this is the set of K indistinguishable points in M, or you can think of this as the set, the space of subsets of M of cardinality K. And yeah, great. Okay, so the idea is that when the manifold is not compact, there's a map that brings in a point from the boundary, pictured here. So we want a map from the configuration space of K points to the configuration space of K plus 1 points, and if the manifold is the interior of the manifold with boundary, with non-empty boundary, what you can do is glue on a little collar neighborhood along to the boundary, and then add a point there. You're not gonna, because we've added this new collar, there aren't going to be any points there, and then you get a configuration of points in the manifold with a collar, which I've called M prime, but that's just homeomorphic to M, so you just pick your favorite homeomorphism that sort of pushes the collar into the manifold, and this gives you a map from K points to K plus 1 points, and this is called the stabilization map. Any questions? Okay, so the theorem due to Dusa-McDuff or originally due to Dusa-McDuff and then later improved by Graham-Siegel, is that this map induces an isomorphism on homology in a range increasing with K. And the stability theorem is an ingredient in our proof of the this will be an ingredient in our proof of that the scanning map for configurations induces an isomorphism and homology in a range. Okay, but I think this theorem is sort of independently interesting. So what it basically says, you should think of it as if I have like a 50-dimensional, if I have a 50-dimensional like movie of points spinning around each other in a manifold, well, and I have 10 million points, well, that movie is equivalent to 100 points do something, and then 10 million minus 100 points are just stationary near the boundary. It's one way of sort of interpreting this theorem. Maybe that's the surge activity part, but it's saying that or I guess when I is 1, it's saying that like any homology class of points doing stuff can be represented by a class where 2 points are doing things and then the rest of the points are stationary. Yeah, so the I guess I'm only going to tell you the proof for orientable surfaces. I'll sort of sketch how you'd prove it for more general manifolds. Yeah, and today we're only going to do the case of R2. Okay. So, oh yeah, so the first step is to prove homological stability for R2. Possibly when I was making the slides, I didn't realize that this would be all that we did today. Okay. So yeah, so let's review compactly supported cohomology. So the compactly supported cohomology is just the reduced homology of the one-point compactification. Yeah, so this is, it's not homotopy invariant. It's it somehow knows about the homotopy type of like the, in some sense, the like part of your manifold near infinity. Okay, so and
I'm sorry to interrupt, but I realized that I don't really understand what I mean, we're taking homology, but I don't understand what the cycles and boundaries are in this configuration setting.
are you saying like what does the cycle look like?
Yeah, exactly.
Yeah, I mean, so I mean, I think of them as just sort of like, it's like a movie of points doing stuff. So like a one cycle might be these 2 points swap places. Or another one cycle might be like this point, goes around a loop in the manifold. And so like a 2 cycle might be the red and the blue happen simultaneously. I don't know if this is in the direction of your question.
Yeah, that's my question. I still don't think that I understand it, but that is my question.
Yeah,
Like whether
so
it's a one cycle or a full cycle or a p cycle, whatever. What determines that? The amount of points moving, or
it's,
what is?
well, it's like the I mean, so here, like the blue and the red, you can each think as like are 2 different maps from like a circle into your space, right? Like the red gives you an embedding of the circle into the configuration space, and the blue gives you an embedding the configuration into the circle.
Yep.
And so so we get 2 maps from like S1 into I don't know how many points there are, 5 or something. And because these are these families are disjoint, that actually gives us a map from S1 cross S1 into this configuration space.
Yeah.
And so then like you could take the fundamental class, you can look at the map on H2, and we know what H2 is. Or we're like H2 of S1 cross S1 is Z. So there's a cycle here corresponding to the fundamental class of the torus, and that maps in here. So that gives you at least a cycle. We don't know if it's 0 or not. As Nick said in chat, the red loop, the red cycle is actually a boundary.
Yeah, if it's just the red loop, I think.
Probably also the blue, but if we add enough.
The blue loop is at least something when you order the points is important. Like you just have meridianal and longitudinal loops in the first homology.
Oh yeah, I forgot they're on. Yeah, so one could figure out. But it's a little bit surprising when you just look at it like the red loop is a boundary. At least I don't know. That surprised me.
Yeah.
So, it's not that obvious. I mean, so there's, yeah, there are sort of calculational methods of computing things, especially with Q coefficients. But yeah, so I don't know. Like, but I don't know if I fully answered your question or if you want to like ask something again, but or maybe let me just say, does it make sense now, like that the red plus the blue gives you a cycle in degree 2 in this space? Because
Not
they're each
really. I don't really understand that. Like in my mind, if we're taking homology of something, we have to pretty much have we have to have a chain complex, and I just don't see it.
Well, I'm just saying that the configuration space is a space, right?
Yeah.
So, so like, we're just like two cycles are just maps, is like a sum of maps from a 2 simplex into the space.
Mm-hmm.
And then you're saying like, well, this doesn't in the, if we took ordered configurations, let's take ordered configurations because that might be easier. Well, that embeds in m to the k.
Yeah.
But this is not a homeomorphism. This is just an inclusion. So, like sometimes cycles in m to the k give you cycles here, but not always. And there are some cycles here that are boundaries there, but they're not boundaries here.
Okay. So so you're kind of like taking singular.
Yeah, take singular homology of this.
It's like singular homology.
Yeah.
That's the way we're thinking about it. Having a space and then our change our maps from the simplest into the space, and and that makes sense because we are kind of embedded in this MK.
Yeah, I mean, just like this thing, yeah. Yeah.
Okay, that's better in my head.
Yeah, this is a topological space, and then and the quotient by the symmetric group is a topological space that no longer embeds into MK, but it still has has the quotient topology. But then there's sort of what you can think of. What I'm saying is you could sort of think of like the homology of the homology. Like you think of intuitively, or at least I do, like the second homology of some space is like a 2-parameter subspace of that space. And in this configuration space, like you can get a 2-parameter family in the configuration space by having like two different 1-parameter families in your manifold. I'm not saying that's the only way, but that is one way. So here, like the blue is a 1-parameter family in M, and the red is a 1-parameter family in M, but then they combine to give a 2-parameter family in the configuration space.
Okay. Yeah, that makes more sense. And our differential in the configuration space, what is it? Like when we take homology, what is the map that we're using?
It's like, I mean, configuration space is just a topological space. Chains are maps from simplices in, And our differential just comes from like restricting the map to the boundary of the simplex.
Right.
But then, then you can ask sort of geometrically, like, what does it look like in terms of these pictures?
Exactly.
And, let's say, you also said, okay, we'll take something that's not a cycle, like this point walks over to the right. Okay, so like this picture describes like a 3-parameter family of points moving around, but now it's not a cycle because the boundary is sort of, like this is like a, this would maybe be a map like across an interval or something. And, and so how would you rigorously view this as a chain? Well, you could subdivide, you could triangulate, triangulate this space, and then you get an element of the chain group, and you ask like, what's the boundary? And then there will be a boundary because, like, of the purple part. I don't know if this is helping or not. Yeah, I mean, you sort of think maybe an easier thing would be just like think about like m to the k and Conf formula. Conf says that, hi of x squared is, of h a of x tensor h p of x.
Mm-hmm.
So, saying like
Okay, yeah, like think of it
squared
in
is like,
terms of m. That's what you're saying.
yeah, so I'm saying like x squared is like the configuration space of 2 points in x. We can call it m, if you want. This is the configuration space of 2 points in m, except, they're ordered and they can collide with each other. They can be at the same point. There's no restriction. So we get a decomposition like the homology, like a 15 cycle in here. One way of getting it would be take a 3 cycle and a 12 cycle.
Mm-hmm.
Parameter, you can think of it as like, okay, one of the points is doing something in a 3-parameter family, and the other point is doing something in a 12-parameter family, and they combine to give you something in a, 15-parameter family. And, whatever, like, I guess every cycle in ordered configuration space gives you a cycle in m to the k, but some of them, but like the ordered configuration space is like a, is a subspace, so there might be sort of extra holes, so some of the cycles might be boundaries in m to the k that aren't boundaries in the configuration space. And then conversely, there might be some cycles in m to the k that don't come from cycles in the configuration space because they necessarily need 2 points to collide. Like if I, maybe I'll just clear everything. If we took like this point going around like that, and then this point, goes around like that, that would give you a cycle in m to the k. But it doesn't give you a cycle in configuration space. It'll give you a 2 cycle in m to the k. But it doesn't give you a cycle in configuration space because like the 2 loops intersect. Any other questions or comments before I move on? Okay. So we're trying to prove homological stability. We're going to start with R2, and the technical tool that we talked about last time is compactly supported cohomology. And we talked, so this is just the relative homology or the reduced homology of the one-point compactification, or equivalently, the relative homology of any compactification of X, rel, the stuff that you've added in. Okay, so, oh yeah, and using that alternate description, we see that last time we saw that you can rephrase Poincare duality for manifolds without boundary as just the homology is isomorphic to the ith homology is isomorphic to the n minus ith compactly supported cohomology. Okay, so we're going to be applying Poincare duality to the configuration spaces themselves. So it's helpful to know when they're orientable. And so there's the following theorem that says, oops, I guess I take rid of the one. So the basically the configuration space is orientable if and only if the underlying manifold is orientable and even dimensional. Oh, I guess I forgot to write even. That's the whole point. And then there's some exceptions. When n is 1, then the configuration space is just the manifold. So, it's orientable if and only if the manifold is orientable. And then, oh, sorry, that's when k is 1. And then when n is 1, like it turns out that configurations of points in a one manifold happen to be orientable, even though 1 is not an even number. I don't know, it's just 1 is small. Okay. I guess it's like somehow the failure of orientation involves like points spinning around each other, and in one dimension they can't do that. Okay, so here's an example where you can see this. So the configuration space of 2 points in Rn, it's homeomorphic to, well, Rn cross an interval cross Rpn minus 1. So how do you think about that? Well, we've got 2 points, so this Rn is their center of mass. This Rpn minus 1 is the line, between the 2 points, and then this is how far the points are away from each other. Yeah, so center of mass, how far away they are from each other, and then the the line that they span after you center their center of mass to the origin. Oh yeah, so the top homology of Rpn minus 1 is z if n is even, or z mod 2 otherwise. So Rpn minus 1 is orientable if and only if n is even, or some low dimensional case. And I guess we didn't talk that much about how orientation behaves with products, but using this, you can deduce that this configuration space is orientable if and only if n is even. Okay. Any questions? Okay. So the next sort of topic is the functoriality of compactly supported cohomology. So in homology, if you have a map of spaces, you get a map on homology going the same direction. And in cohomology, if you have any map of spaces, it's continuous, you get a map in cohomology going the other direction. So compactly supported cohomology is a little bit different. It's only sort of naturally functorial with respect to sort of special kinds of continuous maps. And one kind induces a map that goes in one direction, and the other kind induces a map that goes in the other direction. Yeah, oh yeah, there's some typos. we're getting plus. Okay. So I'm going to screw up if I try to draw a picture of this, but if you basically, if F is an inclusion of an open set, so if F is a homeomorphism onto its image, which is an open set, then, well, there's a map from the one-point compactification of a space to the one-point compactification of an open subspace, where you just collapse the complement of the open subset. Someone could say, oh, maybe you need X to be Hausdorff or something. Great. Yeah, let's assume X is always Hausdorff and paracompact. Yeah, so you can just think about it. There's if you have an open subset, there's a collapse map of one-point compactifications where you send everything out of the open set to a point. And that, that gives you a map on compactly supported cohomology. So the compactly supported cohomology of the open subset is isomorphic to just the reduced cohomology of the one-point compactification. Then you just use functoriality and compactly supported cohomology. Functoriality in regular cohomology to get this map. Then you get X, or that's just the compactly supported cohomology of X. I said this terribly, but are there any questions? Try to draw a picture. I don't know. Let's say this is X, and then U is like a disk. You can, if U is an open disk, then in this picture, the one-point compactification of X is a torus, and the one-point compactification of U is a sphere, and we're just sort of collapsing everything outside of U to a point. Is this map, and then that gives you a map on compactly supported cohomology. Okay, and then similarly, if you have a proper map, which says that the preimages of compact sets are compact, then you just get a map from the one. You get a map on one-point compactifications in the other direction, where you just apply your function to all the points, and like the fact that preimages of compact sets are compact, makes this extend to a continuous map on the one-point compactification, and then that gives you a map the other way. So these are the two kinds of maps in compactly supported cohomology. Okay. And so last time I got confused by this, but eventually I re-understood this. So there's long exact sequence compactly supported cohomology. We proved this by just saying that this is really just like a long exact sequence of a pair involving one-point compactifications. What's the next slide? Oh yeah. But so what's interesting is this map, U is an open subset. So this is one of the kinds of functoriality. And then X minus U is closed. Well, if you have a closed subset, inclusion of a closed subset is a proper map under enough point set topological assumptions. So then, this mapping to that is a proper map, so we get functoriality the other way. Yeah, okay. And the nice thing about compactly supported cohomology is we have this long exact sequence, and what's nice about this compared to Meyerbeer torus, as I said before, is X is literally the union of U and U minus X. We don't need to worry about how they intersect. Compactly supported cohomology takes care of that. Okay, so yes, so to prove that we want to prove that in some range, the ith homology of configuration space is isomorphic to the ith homology of configuration space of one more point. So in a range, I guess we want to prove this in a range. So then it suffices to prove this isomorphism in a range. Oh yeah. So what's the relationship between this isomorphism and that isomorphism? Any guesses? So, oh yeah. So I guess what does this assumption imply? Yeah. So it says the configuration space is orientable. So so the configuration space is an orientable manifold, and what's the dimension? Like what is dim conf km equal to? Maybe an easier question. What is the dimension of m to the k? If n is the dimension of m. Yeah, it's n to the k, and then this is also equal to n to the k because it's a ordered configuration space is just an open subset. So an open subset, is the same dimension, and then the ordered configuration space is a cover of unordered configuration space, and covers don't change dimension. So it's n to the k. So so that's this n to the k. So Poincare, this assumption says it's an orientable manifold. So Poincare duality tells us that these groups are isomorphic and these groups are isomorphic. So we want to prove, so to prove, this purple equal sign, it suffices to prove this green equal sign. Any questions? Okay, so what's and so it's a little bit weird. So this the purple equal sign is comparing two homology groups in the same degree, and but the green equal sign is comparing homology groups in different degrees. So so that's sort of the topic of the next few slides, is how to change that. We'll talk about another problem, and then that other problem will happen to fix this problem. But so to prove stability, we just want to show these two groups are equal. Okay, so here's a question. So this text up here is just recapping the definition of the stabilization map. Does it induce a map on compactly supported cohomology? So remember, we want to show the compactly supported cohomology. This is an isomorphism in range. What's the next slide? Sorry. Yeah, so I guess question, like, is this map proper? And also, is the map or is the map, is it an open embedding and or is it a proper map? Okay, so it's neither. So this point here, I guess I shouldn't have these parentheses, but whatever. This point here is an element of the image. And so if this map were an open embedding, then any point near this point here would be in the image of the stabilization map. But if this black point moves over to where the green point is, that'll be a nearby point, but it won't be in the image. So in other words, the image is not an open set, so it's we don't have that kind of functoriality. Any questions why the image isn't an open set?
Yeah, I don't see it. Could you say that again, please?
Okay, yeah. So, one of the kinds of functoriality for compactly supported cohomology was like maps that are homeomorphisms onto their image, and such that the image is open. So that's what I'm calling an open embedding. And the image of this map is, we can plug in any configuration here, and then we get somehow like any configuration of k points here, but to the right of the blue circle, we only get one point there. Like that's what the image is. The image is any configuration to the left and one point to the right. And I'm saying that's not open because this black point can move, and then it won't be, in a small open neighborhood, this black point can move, and it won't be in the image.
Yeah. Okay, thanks.
And then you might wonder, okay, is this map proper? And let's say we move this to the preimage of compacts need to be compact. Let's say this this black point moves. We have an embedding of an interval, which is closed interval, which is just this black point moves in a closed interval. And what's the preimage? We sort of get like this half open interval. The blue is a picture of an embedding of a closed interval, and the preimage is going to be a half open interval. Maybe, I guess it's a half open. Is that wrong? I've confused myself. The map is not proper, but the preimage. Yeah, okay, so okay, I don't know how to draw a picture of it. I'm going to try to say it in words. So, okay, so we get a map. You get a map. The blue is a picture of a map from a closed interval into this configuration space. What is the preimage? Well, on the right endpoint of the interval, the preimage is just this configuration space. So the preimage is a singleton set. Then for a while, the preimages are empty. And then we cross back into the non-collar part of the manifold, and the preimages become a point again. So the preimage of a closed interval is going to be a point union a half open interval, which is not compact. So the map is not proper. I'm happy to say it again, but it's also a little hard to draw. Okay, so yeah, so this map was fine for thinking about homology because it's a continuous map, but it doesn't play nice with compactly supported cohomology. So the fix that we're going to use is we're going to build this map capital T from the configuration space cross Rn into the configuration space of one more point. So what's the idea? Well, we're going to view Rn as the configuration space of one point in a ball. And what you do is you just sort of embed, so we have a point in Rn, which is like the same data as a point in this disk, and you embed the disk into the collar, and then wherever your point is, that's where you put the point, and then you have these points over here. Yeah. Any questions? So yeah, so what we're doing is we're just extending this map to a map from the configuration space across Rn, and now it becomes an open embedding. Somehow, you might think like, if you think about it, it's hard for, this is a k-dimensional manifold. This is a n times k-dimensional manifold, and this is an n times k plus 1 dimensional manifold. So this manifold is bigger dimensional than that manifold. So it's hard for the image of this to be an open set there. So what we do is we're just replacing it by a homotopy equivalent manifold of the right dimension. And then it's easier for this to be an open embedding because they're the same dimension. Okay, so this is an open embedding, so it induces a map on compactly supported cohomology in the direction we want. Any questions? Yeah, so how do they compare? Well, if you think about it, so if you pick, you can include configurations of k points into configurations of k points across Rn by picking your favorite point in Rn. This composition with capital T is just the lowercase stabilization map. So up to homotopy, these maps are the same. Like this first map is a homotopy equivalence, and then the composition is lowercase t. So it suffices to prove capital T. If we can prove capital T is a isomorphism in a range, we know that lowercase t is. Yeah, so we should think is just for the purposes of compactly supported cohomology, it's better to change our model so that the domain and the range are the same dimension, but capital T and lowercase t homotopically contain the same information. Crossing with Rn doesn't change things. Up to homotopy, it does change compactly supported cohomology, though, because that's not a homotopy invariant. Okay, oh yeah, so the next question is, how does the compactly supported cohomology configuration space of K points in M and K points in M cross Rn compare? Yeah, so if you think about it, crossing with Rn and then taking 1-point compactification has the effect of smashing with a sphere or just suspending. So draw a picture. Okay. We got an interval. That's going to 1-point compactify to a circle. And then if you cross the circle with with R, then it'll give you, all the blue is R, then you cross it with R and you get the red square, and then you 1-point compactify, and then you get a sphere. So the light blue compactifies to the circle, the red compactifies to the purple sphere. So yeah, I guess what I'm saying is that crossing with Rn and then 1-point compactifying is the same thing as suspending n times. So here we crossed with R once, and then the effect on 1-point compactification is to suspend once. We suspend the circle to get the sphere. And so suspension just shifts homology. So, so this tells you that crossing with Rn just shifts compactly supported cohomology. Any questions? You could also think about this isomorphism as there's a Conf theorem for compactly supported cohomology, and you can just calculate the compactly supported cohomology of Rn because it's the reduced homology of a sphere, and then Conf will tell you that there's a shift. So now we have this great diagram that is telling us very little, or not, or sorry. This diagram is like obvious, but it's so large that it's intimidating. And then I'm going to flip the slide before people have the chance to process it. So I don't know what the correct solution is. Yeah, so, okay, so maybe I'll just talk about it. And so we wanted to prove that that this lowercase t was an iso, up to homotopy. That's the same thing as capital T, because crossing with Rn doesn't change things up to homotopy. And then now these are both manifolds at the same dimension, so we can apply Poincare duality, and there's no shift. I guess I wrote it differently, but these two numbers are the same. And then the suspension, or the isomorphism tells us that this group is isomorphic to that group, and the diagram commutes. So we want to show this map's an iso. It will suffice to show this map's an iso. Yeah. Any questions, or anyone want like another 15 seconds to look at this slide? Great. Okay. So we're going to compare configuration spaces to the symmetric product. The k-fold symmetric product is of the space X is just X to the k mod the symmetric group. So what you should think about is, we have like ordered configurations maps to m to the k. And then this has a quotient map to unordered configurations. And then, this has a quotient map to sim k. Yeah, so, you should think of it as like it's the unordered version of m to the k. So it's like configuration space, but points are allowed to collide. And we've sort of seen this space before. So the free abelian monoid in a space, so n of x, is just the disjoint union of the symmetric products of k to the x. So what we're thinking of, you should think of sim k as the space of points in x, but now they're labeled by natural numbers, and the sum of the natural numbers adds up to k. Yeah, so this is a picture of an element of sim 50, because 40 plus 1 plus 9 is 50. Yeah, so it's this is the configuration space of 50 total points that are indistinguishable, but they don't need to be distinct. So we might have 40 points all sitting on top of each other. Yeah, so you can think of it as labeled, or there's just 40 of them and they're unlabeled, but we're counting how many of them happen to be sitting on top of each other. Okay. And yeah, so what's going to make R2 special is the following proposition. So the k-fold symmetric product of R2 is R2 to R to the 2k. So this is definitely false in higher dimensions. I think it's true if you replace 2 with 1, but if you replace 2 with 3 or 4, it's definitely false. Yeah, so what's the proof? Well, sim k R2, R2 is homeomorphic to C. You think of it as C. And what is sim k C? Well, this is the space of monic degree k polynomials parametrized by their roots. So if you degree k polynomial, its roots are its roots counted with multiplicity give you an element of sim k. On the other hand, c to the k, which is r to the 2k, you can think of as the space of monic degree k polynomials now parameterized by their coefficients. So the homeomorphism is given by like sending a polynomial parameterized by its roots to a polynomial parameterized by its coefficients. So I guess in the this direction, we know how to write down the map explicitly. But it's a homeomorphism because of fundamental theorem of algebra. And we can factor polynomials. Any questions? Yeah, so what we're going to do is we're basically going to reduce homological stability to stability, or we're going to reduce stability for compactly supported cohomology. See what my next slide is. So we're going to reduce stability for compactly supported cohomology of configuration spaces, the case of symmetric products of R, and case of R2, and then we're going to use the fact that it happens that symmetric products in the case of R2 are manifolds. In general, the symmetric product of a manifold is not a manifold, but it is in dimension 2. So how do we prove this? Well, by Poincare duality, because we just check this is homeomorphic to the Euclidean space, so we have Poincare duality. Proving stability for, or proving that this map is an iso on compactly supported cohomology is equivalent to it just being an iso on regular homology, but all of these spaces are contractible. This is R to the 2k, this is R2, this is R to the 2k plus 2. What is this capital T? I guess my implicit here is the statement that the, where is this map? This map extends to a map on symmetric products. So, it makes equal sense if these points are labeled by numbers. Any questions? Great. Okay. So now I'm going to tell you a filtration of symmetric products where the filtration differences will look like configuration spaces. So okay, here's a great fact. If you have a number, let's say you have a natural number, it can be written uniquely as an even number plus either 0 or 1. Okay. Great fact. What does that say? It says that if you have an element in some symmetric product, so it's an element in n of x, then it can be written uniquely as an element y plus 2z, where y is an element of the configuration space and z is an element of the symmetric product. So we have this element of the symmetric product, or element of n of x. So it's like maybe this point's labeled by 1, this point's labeled by 40, this point's labeled by 9. Well, 2 of these numbers are odd. So for the odd numbers, we're going to have an element of the configuration space. And then for all the numbers, we're going to take the lowest or the highest even number less than or equal to that number and then divide it by 2. So this is isomorphic to that. Sorry. This is equal to that. And so I didn't have a subscript in Conf K. That means disjoint union over all of them. Any questions? So this statement that kind of looks intimidating is just the statement that every number is either twice a number or twice a number plus 1. So for the The odd ones, we get this contribution in the configuration space. And this 2 is exactly the 2 in the like slope 1/2 stable range. Okay. So we're going to define a filtration of symmetric products. So just some notation. Let's just say if z is in sim k, we'll just say the degree of z is k. If you think of it as a polynomial, you know, that's would be the degree of the polynomial. So we're going to filter sim k by these subspaces sim k superscript d. And so, you know, every element in sim k can be uniquely written as a y plus 2z, where y, all the points are distinct. And z is in the symmetric product. And so we're going to filter it by the degree of z. Next slide. Maybe we'll go back to this picture. So here, this is y, and this is z. So I guess here, the degree of z is 24 or something. So this would be an element. This would be an element of sim 50 24, but it wouldn't be an element. I forgot. What's the next slide say? Degree. If it's bigger than or equal to or less than or equal to. Degree bigger than or equal to. So this is not, you know, this is not in sim 25 50. Okay. Tell me if I flipped it and I meant to say not in sim. I think this is correct. Not in sim 23. Yeah. Okay. So, okay, so the first, oh yeah, so this is just recapping the definition. It's easy to forget. So the first claim is that sim superscript 0 is just sim. The, you know, degree being greater than or equal to 0 is no condition. And then the next comment is that these things are empty when d is big. Yeah, so why are they empty? Any thoughts on why this is true? You know, so you know, like, is 3 equal to 0 or 1 plus 2 times some number that is at least 2? No. I mean, you know, this is empty just because what this is saying is that, you know, counted with multiplicity, z has d many points, so 2z is going to have 2d many points, and if 2d is bigger than k, you know, so like this is supposed to be degree k, but it's also going to be the degree is also going to be equal to like the degree of y plus 2 times the degree of z So we get the equation like this tells us that K is greater than or equal to 2D. So if 2D is strictly bigger than K, then no configurations can satisfy it and it's empty. Okay. And then the next comment is that if you look at the differences in the filtration, you get that so this is if you're in sim superscript D but not in sim superscript D+1, then that tells you that the degree of Z is exactly equal to D. So if the degree is exactly equal to D, then what's the information? The information is just Z and Y. And Z is Z has degree D, and then Y has degree K minus 2D because the total degree is K. So the differences become are symmetric products across configuration spaces. So the idea is, okay, what big picture, what's going on? We know stability for symmetric products, and then we filtered it by, I don't know if they're open or closed sets, but like they're one of them, and the filtration difference is going to be elements of the symmetric product across configurations. So we're going to, basically what we've done is we've written symmetric products as in terms of symmetric products across configuration spaces. And then if you think about it, like conf K will show up once, and then a bunch of smaller configurations will show up. So we've written some space we understand as the union of a space we're interested in. So when D is 0, this is the space we're interested in. And then, sim Ds, which we understand, and then configurations of smaller points, which by induction we understand. So we're interested in this when D is 0. And so so that's the idea. Any questions? When I first read this proof, I was just like, I guess we're not done, and we probably won't finish today, which is fine. But it's just going to be like a trillion Poincare dualities, and I couldn't see where what we're actually using and how it worked. Okay, so we're going to prove by we're going to induct on two different statements. So the first statement is that the first statement is that is going to be stability for configurations of points in Rn. And so it's going to be the statement that in top degree, or when I is equal to n over 2, we get a surjection and homology, and in lower degrees we're going to get an isomorphism for a configuration space. So that's the AK statement, and then the BKD statement is stability for sim KD as we increase K. We want to prove A, but this B statement will be useful auxiliary statement. So okay, so one of the base cases is that BK0 is true for all K. So BK0 is the statement about stability for sim 0, 0K R2, but that's just the same thing as sim, which is the same thing as R to the 2K. So we know that BK0 is true for all K. Yeah, and then the next part of the induction is that, or the induction beginning, is that BKD is true for large D. So we know that it's true when D is 0, and then we're going to prove that it's true for large D, and then we're going to induct downward on D, and then, I don't know. Okay, so why is this true for large D? Well, what did we say? When D is larger than twice K, they're empty. So if D is larger than, if 2D is larger than K plus 1, then, if 2D is larger than K, the domain space is empty, and if it's larger than 2D, if 2D is larger than K plus 1, the range space is empty. So this is, this is just a map from an empty set to an empty set, induces an isomorphism on homology. Great, that's true. Any questions? Yeah, so, okay. So we have the statement AK, which is stability for configuration spaces. Maybe we also need A0 is true. A0 is pretty clear though. A0, if you plug in K as 0, this is a point. And this is R2, and so it's a statement that a map from a point to R2 is an iso, is a surjection on H0. So a map from two connected spaces induces a surjection on H0 is a true statement. Yeah. So we're going to have two different induction steps. One induction step is going to be that BK D plus 1 and AK minus 2D imply BKD. And then the next induction step is going to be BK0 and BK1 imply AK. And if you think about it, this is enough, that if you have this plus our induction beginning, you get that all of these statements are true for all K and D. And then what we're interested in is in AK. Yes, okay, so probably I will technically finish, but I think I will have lost people, but it's no steps are hard. This proof is sort of annoying because no steps are hard, but it's hard to figure out where we did anything non-trivial. Yeah. Okay, so one of the two induction steps we need is that BK D plus 1 and AK 2D imply BK. So what's the proof? So, you just use these filtration differences and you get, so this minus that is this. Well, something is open in something. I think this is open in that. This is either open in this, or I flipped it and this is actually a closed subset, and then this sequence should go the other way. But great, let's assume this is open in that, and if you disagree, tell me. So so you get a long exact sequence in homology coming from we call it long exact sequence in compactly supported cohomology coming from open subspace, inclusion, and then the complement. So we get this long exact sequence, and we know, and you're going to map this to the thing for K plus 1, and we know by assumption, this assumption tells us we have stability here. This assumption tells us we have stability here. Because the filtration difference is just R to the D configuration space. So here, this is just a shift of the homology of configuration space. So our, induction hypotheses imply we have stability here and here, and we want stability there, and then the 5 lemma gives us that. And so the other argument is similar. So if you look at the I flipped it. All this is backwards. This is closed. So it's closed, so the map should go the other way. But whatever. I think it's closed. Yeah, same argument applies though. Maps go the other way. Yeah, so if we know stability here and stability here, we get stability here by the 5 lemma. Yeah, so by saying the 5 lemma, I'm saying look at the map from this long exact sequence to the long exact sequence for k plus 1, and you'll get that it's isomorphisms or surjections in 4 out of the 5 spots, and then you get an isomorphism or a surjection in the last spot. Okay. Any questions? I'm going to stop the recording.